take a concave mirror. A concave mirror is a curved mirror in which the inner part is reflecting, the inner side is reflecting. And if you incident a parallel beam of light, then these rays of light after reflection will get focused at a single point. They will converge at a single point called as the focus of that mirror. And you can get parallel rays of light from any source which is far away. Something like the sun or anything which is far away, the rays of light from that can be assumed to be parallel. In this video, what we'll do is we'll look at some applications of this concave mirror. Where do we use them in our daily life? All right, so let's begin. One of the applications we can see is in microscopes. So if I just show you a compound microscope, let me just show you that. A compound microscope over here. You may or may not have used it, but if you have, then you know that you keep your slide, whatever you want to observe, or somewhere over here, and you need that slide to be lit up. Otherwise, you can't see it through the microscope, isn't it? And the way we light that slide up is by using a mirror over here. And what this mirror does is that it takes in the sunlight and then focuses all that sunlight right at this slide. Now, I don't think in this picture the mirror is aligned properly, but if you align it, then we can focus all the rays of light from the sun to a single point, and we can make that focal point, that point where it gets focused, right on that slide, and the slide gets illuminated. All right, so there's a concave mirror down over here. It's a concave mirror. So next time when you're using a compound microscope, just touch that mirror, and you can feel the concave part of it. Another similar place where you can see this is in your satellite dishes. Not satellite dishes, I'm sorry. These are dish TVs. These are the receivers of your dish TVs. They're supposed to receive the radio signals, but you can see that there is a concave reflector over there. Now, this is not a reflector of visible light. This is a reflector of radio waves. Now, radio waves are pretty similar to visible light, except that you can't see it, but everything is the same. Almost all its properties are pretty much the same. And so these radio signals come from some radio tower which is far away. And as a result, we can also assume that the radio signals we get over here, let me draw some radio waves. The radio waves that come over here, we can also pretty much assume that they are, let me draw it over here, it's easy to see. Those radio waves, you can assume they are, okay, let me choose. Okay, fine. So the radio waves which are coming over here, we can assume that they are parallel to each other. And when these parallel rays go and hit this particular reflector, it reflects these radio waves to a single point. As you can see, all the radio waves get reflected to a single point, and that point is the principal focus, and it's that point you are going to keep your radio receiver. And as a result, the receiver will receive a very strong signal, a very highly concentrated signal of radio waves, and that signal will now then be sent to your TV, and you can watch television. One more application of this same concept is in solar cookers. We can use this principle to actually cook food. So whatever food you want to cook, you can keep it at the focal point of a giant mirror. And then when the sun is at the right place, like, during the noon time, when the sun is right above you, we just, orient the mirror in such a way that all the parallel rays of light are being focused on the food that you want to cook. And then using the concentrated power of the sun, we can cook the food. That's the idea behind solar cookers. Another application, it's a little bit different, is found in flashlights or headlights of a vehicle. If you look at the back part over here, they're reflecting. That is a concave mirror back there. Why are we using a concave reflector here? Are we trying to focus the beam of light here as well? Actually, no. In fact, over here, we're trying to do something exactly the opposite. So if we come back to the ray diagram, one of the cool properties of these rays is that we can reverse these rays and the diagram still holds true. What I mean is, if you look at this ray, this is the incident ray and this is the reflected ray, right? Now, what I'm trying to tell you is we can reverse this, meaning if this is the incident ray, then this would be the reflected ray. Let me just show you what I mean. So I'm just going to reverse all the arrow marks. Look at the diagram carefully. Just going to reverse all the arrow marks. And I'm saying the diagram still holds true. So let me just draw that over here. And the reason that is true is because, think about it. Even if we interchange the incident ray and the reflected ray, the angle of incidence and the angle of reflection will change. Let me just draw that. The angle of reflection, before this was the angle of reflection, and this was the angle of incidence, but now this will be the angle of incidence, and this will be the angle of reflection, because this is the incident ray and this is the reflected ray. But it doesn't matter because they're both still equal to each other. And so the rule of reflection will still work, isn't it? And that's one of the cool things about reflection, all right? You can always reverse the rays of light and it'll still hold true because the rules of reflection will still hold true. Now, what does this mean? This means, I mean, look at this. This means that if you have a point source kept right at the focus of that mirror, of that concave mirror, and that source will now start giving light in all the directions. If you consider the light that falls on the mirror, after reflection, all the rays of light will end up becoming parallel to each other. Exactly the reverse. Before, the parallel rays are being concentrated at a single point. Now, a ray of light emanating from a single point is becoming parallel to each other. Okay, and so what's the use of this? Well, whenever we want to create a highly directional beam of light, well, we can use a concave reflector. That's exactly what's happening over here. So here is the bulb. Over here, you can see a tiny bulb over here, right? And that bulb is placed right at the focus of this entire reflector. And so if you look at the rays of light that are coming forward are just coming forward. Nothing will happen to them. But the rays of light that are going back, they hit the mirror. And because of this property, because the rays of light are emanating from the focus, these rays of light, after hitting the mirror, they get reflected forward. And as a result, this flashlight ends up producing a beam of light which is directed forward. So we've seen that, right? Flashlights produce a forward beam of light, pretty directional beam of light. And that's possible, that's happening only because there is a reflector behind. And the same thing is working true. This same thing also holds true for the headlights of a vehicle. All right, so what we did in this video is we looked at a couple of applications of concave mirrors. And all the applications we looked at were based on one principle, that parallel rays of light, when they hit the concave mirror, they all get focused at a single point. And of course, its reverse is also true. I just like to talk about one last application before ending this video. There's also a very interesting application, not in light, but in sound. The same thing even works out for sound. Even sound can reflect, and even for reflection of sound, the angle of incidence and the angle of reflection turns out to be true. And so the application comes in acoustics. If you're in a large hall and you want to address an audience, and then we can assume that the audience is sitting somewhere, let's say the audience is sitting somewhere over here, and you have this large hall over here, and suppose you are the speaker and you want to channel your audio, you want to channel your sound in the forward direction and not sidewards, then what you can do is you can put a large concave reflector behind you. Now this would be a reflector of sound, not light. And that will ensure that any sound that goes back will get reflected forward like this and will be channeled towards your audience.